Have you ever tried to hear a single pin drop in the middle of a packed stadium during a rock concert? I mean, it sounds impossible, right? Well, that's pretty much what astronomers are trying to do every single day. They are literally tuning their instruments to listen for the absolute faintest echoes from the most powerful, most violent events in the entire universe. We're talking about ripples in space-time that have been traveling for billions of years. So the question is, how on earth do you even begin to hear something like that?
Right, and that's the challenge. These aren't echoes of sound. They're gravitational waves, which are actual physical ripples in the fabric of space-time itself. And being able to detect them is, without a doubt, one of the biggest technical hurdles we've ever faced.
So, to really get your head around the solution they've come up with, you first have to appreciate just how big the problem is. These signals, you can think of them as cosmic whispers. They're the tiny, leftover vibrations from absolutely colossal events, like two supermassive black holes smashing into each other.
And that analogy, a whisper in a crowded stadium, that really gets to the heart of it. The signal itself is incredibly faint, and it's buried in this universe of background noise coming from everywhere, from Earth, from space, you name it. The real trick is figuring out how to pick that one single whisper out of a roaring cosmic crowd. Now, scientists have a name for this. It's called the signal-to-noise ratio, or SNR for short. It's pretty simple. A high SNR means your signal is loud and clear, easy to spot. But the events we're most interested in, the ones that are the furthest away, the oldest, they have a really low SNR. And those are the whispers we're desperate to find.
So how do you build a better cosmic ear? Well, the first part of the answer is some seriously impressive new hardware. I'm talking about the next-generation Einstein Telescope.
So, unlike the detectors that came before it, the Einstein Telescope, or ET, has this really unique triangular shape. And that's key. It's not just one giant detector, it's actually three of them, all working together in perfect harmony.
And this design gives it some incredible advantages. For one, having three detectors gives you multiple points of view on the same event, which helps you be absolutely sure that what you're detecting is real. Its arms are a massive 10 kilometers long, which makes it way more sensitive. It's also built deep underground to escape all the vibrations and seismic noise from the Earth's surface. And maybe most importantly, it's tuned to hear lower frequencies, and that's the exact range where we think the universe's oldest secrets are hiding. But here's the thing. Amazing hardware is only half the battle. The truly game-changing part of this whole story is how scientists are teaching an AI to listen with all three of ET's ears at the exact same time, giving it something like three-dimensional hearing. Okay, take a look at this. This is the raw data from each detector. It looks like static, right? Total noise. The AI has to find a signal in that. Can you spot the cosmic whisper in there? Yeah, me neither. And that's exactly the problem. Traditional methods just couldn't do it, not reliably anyway.
But this is where the genius idea comes into play. The researchers thought, what if, instead of trying to listen for the signal, we could teach an AI to see it? So first, they take each of those noisy data streams and turn them into a visual map of frequencies over time. That's called a spectrogram. Then, and this is the clever part, they assign each of those three spectrograms to a color channel, red, green, and blue. And finally, they just stack them on top of each other to make a single color image.
And the result is, well, it's remarkable. Because the background noise is totally random in each detector, when you combine them, it all just kind of washes out into a gray mess. But the real signal, that little chirp pattern you see, that's present in all three detectors. So it lines up perfectly and just pops right out as a clear visual pattern. It's like giving the AI depth perception, so it can instantly tell the difference between a real event and just a random glitch.
So from there, all they had to do was train a really powerful image recognition AI, it's called ResNet, to do just one job: spot that specific visual pattern. You can think of it like a world-class bird watcher who can recognize a rare bird from a single fleeting call. Except in this case, the AI has been trained to see the visual fingerprint of two black holes colliding.
Okay, so that's the theory. It's a fantastic idea, but does it actually work any better? Well, that's where the results get really exciting. The scientists decided to put the new method to the test against the old traditional approach.
So they set up a direct head-to-head comparison, a bake-off, if you will. In one corner, you've got the old method, trying to analyze that super noisy data from just one detector. And in the other corner, you have the new method, giving the AI that clean, combined, three-color image to look at.
And the results are they're stark. I mean, look at this graph. The green line, that's the new three-detector method. It is consistently and dramatically more accurate than the old single-detector method in red. And look at where the difference is biggest. It's for those really faint signals, the ones with the lowest signal-to-noise ratios. That's exactly where we needed the help.
And if we're going to put a number on it, for the absolute faintest, hardest to find signals, this new method was an incredible 24.5% more accurate. That's not a small improvement. That is a massive, massive leap forward in our ability to detect these things.
We can also see how many mistakes each method made. Look at the chart on the left for the single detector. See all those off-diagonal squares? Those are errors, real signals that got dismissed as noise and noise that got mistaken for a real signal. But now, look at the new method on the right. It is almost perfectly clean. For any signal that had even a moderate strength, the AI made 0 mistakes. It was absolutely flawless.
So, what does all of this actually mean for science? What's the big takeaway? Well, this isn't just some small, incremental improvement. This combination of brilliant hardware and even more brilliant AI is kicking off a completely new era for astronomy. The impact is just so clear. In a simulated run of data, the old method missed over 700 gravitational wave events simply because they were too faint to be found. They were lost forever. The new 3-detector AI, it missed far, far fewer, successfully spotting hundreds of those cosmic whispers that would have otherwise just been lost in the static.
So why does this matter so much? Because it's huge. It means we can now detect events happening way deeper in the universe. In one of their tests, the system found a black hole merger at a truly mind-boggling distance of 86.6 gigaparsecs. We're talking hundreds of billions of light years away. And what's even more impressive, it can do all of this analysis incredibly fast. In fact, the researchers themselves noted that their system could crunch through a full hour of data from all 3 detectors in less than 5 minutes. That kind of speed is absolutely critical for sending out alerts to other telescopes around the world, so they can turn and look at where these cosmic whispers are coming from.
So when you step back and think about it, we've effectively taught a machine to see the invisible, to pick out a single unified pattern from 3 different perspectives, a pattern made from the vibrations of space-time itself. It really leaves you wondering, now that we have this powerful new sense, what secrets from the dawn of the universe is it finally going to show us?